Once again, good morning to one and all present here. On behalf of the Department of Mathematics, Sir Theagaraya College, I welcome you all to the webinar titled Glancing Ramanujan's Mathematics. First of all, I thank our Secretary, Kumarasamy Sir, our Principal, Dr. Sendil Kumar Sir, and our management for giving us this opportunity to conduct the webinar. I warmly welcome our speaker, Professor Sivaraman Sir, Associate Professor of DG Vaishnav College, Arumbakam, Chennai. And also thank him for readily accepting our invitation and deliver his presentation online. Welcome you, sir. I welcome all the participants, faculty member of our college, teachers, research scholars, and students, and thank them for their enormous support to join the webinar. Once again, I thank you all. Welcome you all. I request our HOD, Dr. Ramamurthy sir, to introduce the speaker.
Hello, good morning to all. It is a great pleasure to introduce the speaker of the webinar. Professor Sivaraman is a well-known person that there is no need for an introduction to be given. Nevertheless, let me give you a short profile to have a glimpse about him. Dr. R. Sivaraman has been conferred with the National Award for popularizing mathematics among masses in 2016 by Department of Science and Technology, DST, Government of India. He was conferred with Indian National Science Academy Teaching Award for the year 2018. He has also received 2 state government Best Science Book Awards in 2011 and 2012. For his contribution to mathematics, he has won more than 30 awards so far. He has provided more than 300 lectures conveying the beauty applications of mathematics. He has published more than 30 research papers in mathematics. He was member of editorial board for more than 10 journals in mathematics. He was a member of the textbook writing committee, Tamil Nadu School Education Department, for preparing revised mathematics textbook for 11th standard and chairperson for 10th standard. He writes articles and provides puzzles for famous newspapers like the New Indian Express, Times of India, the Hindu School edition paper, Tamil Hindu, Dinamalar Pattam newspaper. He has also contributed several articles about mathematics in monthly magazines like Ariviyal Oli, Chennai Report, Arumbu, and continues to contribute more. He is currently the editor of the journal Junior Mathematician, a quarterly magazine for school students published by AMT. For the past 20 years, he teaches most deserving and poor students and made their life to have better living. In view of spreading mathematics among everyone, he had initiated an exclusive charitable trust by Mathematics Association. Serving the poor and needy students was his life motto. I am happy to have this speaker in our session. Thank you. Over to Dr. Nalide.
Thank you, sir. I would like to add on to this HOD speech. Do you all know about the number 1729? Yes, 1729 is a special number. Is called Ramanujan's number. Since it is the smallest number expressible as a sum of 2 positive cubes in 2 different ways. 1729 is 1 cube plus 12 cube is also another one is 9 cube plus 10 cube. But why am I stating this number at this moment? Since our speaker email address is rshivaraman1729@yahoo.co.in. This shows that our speaker, Professor Sivaraman, has an exceptional interest towards Ramanujan and mathematics. He is the right person to present the webinar about the great mathematician Srinivasan Ramanujan. Now, I request Professor Sivaraman sir to deliver the presentation titled Glancing Ramanujan Mathematics. Now I hand over the session to the speaker, Professor Sivaraman sir. Thank you. Sir Sivaraman sir.
Madam, my video is not starting.
So now I'll make you a host.
Have you
one
shared
second, sir. So now you are the host. You can share your screen. So you can start video also.
Okay. So, good morning
Okay,
to
sir.
all.
Visible. Okay.
I take great pleasure in giving this presentation about glancing Ramanujan's mathematics. I had been lecturing about the great mathematician Ramanujan for the past several years. So, I'll be sharing what little I know about the great mathematician, seeing through his notebooks, through his jottings, and whatever he felt he recorded in his notebook. I will be sharing few of those things with you and make you feel very happy. So I straight away go to the presentation so that you can know much better. So if you see this magic square that is drawn for today's date,
So sorry to
this is
disturb you. Only one.
yes,
Hello.
is it audible? The first row contains the date of birth of Ramanujan, 22/12/1887, and you see there is a puzzle that I have written. This puzzle is created along Ramanujan's uh, ideas. Like not exactly what Ramanujan did, but seeing Ramanujan's formulas, I created this puzzle. You will be soonly knowing what is the answer for this puzzle. This is nested square root problem. We will discuss about this. Probably you might be knowing yourself after I give some clues to you. Now, this magic square is very special because I made it yesterday. The first row contains uh, Ramanujan's birthday, and this blue colored cells, namely, if you look at this 8, 6, and 20, if you look at this 8, 6, and 20, forms today's date, 8 June 2020. And this number 65 is called the Ramanujan number because it is written as sum of squares in two different ways. Namely, it is 1 square plus 8 square as well as 4 square plus 7 square. Ramanujan number 1729, which Madam told, Nalini Madam told just now, is sum of two cubes in two different ways. So this class of numbers form what is called, what mathematicians today call taxi cab numbers. Okay, and this numbers in color 54 and 36 are what is called highly composite numbers, which Ramanujan's very favorite area of research. I will share about the detail later. So this 30 and the other numbers are formed in such a way that the whole thing forms a magic square in which row sum, column sum, diagonals, as well as other cells like four corner cells, four middle cells, this four middle cells, any 2 by 2 uh, cell like this 4, this 4, this 4, and this 4. This 4 will form a magic square. The central four numbers form again 139, sum of 139. And if you look at 139, that itself forms a pattern. So one thing that you find in Ramanujan's mathematics is doing math with pattern. The most thing that I admired in Ramanujan's formulas were most of them were written with some hidden pattern. And God had made such a way that the row sum or column sum of Ramanujan's date of birth adds up to 139, which is itself 3 power 0. The digits of 139 are 3 power 0, 3 power 1, 3 power 2. They are in geometric progression. So such a wonderful thing you find in Ramanujan's date of birth square. This was formed by myself yesterday, so that all special numbers are put into fit to form a magic square. This picture was formed by my friend J. Prabhakar. I shared this picture in our Tamil book Engalin Anbar, published by Pi Mathematics Association. The wonderful thing about this particular image is that it starts at 1 in the eyebrow. You see, it starts at 1 in the eyebrow here, and then it goes on continuously, and it ends with 499 and 500 at the collar of the shirt. This is 499 and this is 500. ends here. So the first 500 numbers are chosen in such a way that Ramanujan's picture was drawn. Now let us go to Ramanujan's mathematics. We start from elementary things and go a little higher and higher so that we come to know what he did as time progresses. Now, when he was in school doing his fourth form, which is nearly eighth or ninth of today's equivalents, uh, Ramanujan was probably doing his eighth or ninth class when he was posed with this problem by his friend, a senior to him, 1 year senior to him, named C.V. Rajagopalachari. He was asked to solve the equation root x plus y is 7 and x plus root y is 11, for which Ramanujan immediately gave the answer, namely x is equal to 9 and y is 4 as visible to you. And if you can substitute here, you can see the root over 9. Root of 9 is 3, 3 plus 4 is 7, and 9 plus root 4 is 9 plus 2 is 11. So automatically forms a solution. Of course, this solution was not given by Ramanujan. He just guessed the answer. For the sake of better understanding how to arrive the solution, I had given a short method here. But that is a characteristic of Ramanujan. I mean, he doesn't bother about the methods. He
So some
always
once again, sir,
get the answer.
some of them are waiting in the room. You just admit them.
Okay, so I will wait for some time.
No, no, sir. You should admit.
Oh,
Below that column, one admit will come in the
um,
participants.
how much, madam? I mean,
Admit all. You just press admit all.
admit all. Can I give?
Yes, sir. Yes, sir.
Is it okay now?
Oh, okay, sir.
Okay, madam.
Okay, sir. Continue, sir, please. Continue. Sir.
Point is getting struck for. So at much earlier age, when Ramanujan was probably doing his sixth or seventh class, first form or second form probably, he was taught division uh, in the mathematics class, and the teacher said that if you have say 6 bananas and if you want to distribute among 2 people, assuming that each gets equal share, how much would each get? The teacher said each would, students said each would get 3, and therefore teacher said that is a reason why 6 divided by 2 is 3. So he imparted uh, saying that division is an equal sharing process. Division process is equal sharing. So as you see, 6 bananas divided upon 2 people, 2 students, assuming that each get equal share, they get 3 each. So this explains the process of division, saying that 6 by 2 is 3. This is how he gave some other examples also, just sake of understanding. 18 objects are there distributed to 3 students equally. So each get 6 here. And there are 12 cakes here distributed to 3 students. Each would get 4 cakes. So division is an equal sharing process. Now, teacher then proceed to say that if I have 6 chocolates with me and if there are 6 students, if I give 1 to each, how many would get? Uh, each, assuming that each would get equal share. There are 6 chocolates and 6 students are there. How many each would get if they assume that there are equal sharing? Students immediately answered that each would get 1 because 6 by 6 is 1. And he said, if I have 2 chocolates and if I distribute to 2 students, how many would each get? And the answer is still 1. And then teacher pointed out that if the number of objects and number of students are equal, then the share would be 1 to each, assuming that equal sharing. So that explains the fact that any number divided by itself is 1, namely x by x is 1. So this is how division was taught in those days when Ramanujan was studying. I don't know how division was taught today, but in those days it was done like that. Um, it was a very nice explanation by the teacher. But you see, Ramanujan immediately raised his hand and said, "Sir, I have a doubt that if there are no objects and no people, there are no bananas and no students to give, he could get one each still?" This was questions which baffled the teacher. He doesn't know the probable answer immediately. Then he guessed what was Ramanujan actually trying to do. What Ramanujan was trying to ask was, is 0 by 0 is 1? Because there are no objects, so numerator is 0. No students, the denominator is 0. If there are no objects and no people to give, there's no question of sharing at all. Probably, practically speaking, there's no need of sharing. But what Ramanujan was trying to figure out was, if, as per the teacher's claim, if the objects and number of people to distribute are equal, then the ratio should be 1. Now, is that principle still becomes true when 0 divided by 0 is that is uh, that is still 1? Now, this question was very deep in the sense that when you do calculus, you study about limit delta y by delta x for dy by dx, and you approach delta x tends to 0. So both the numerator, the y change in y as well as change in x goes to 0. So the ratio goes to 0 or 0. So what Ramanujan was trying to think was limiting process, not just in numbers. So this idea of limiting process and knowing to know what could be the answer of a ratio when both are very small was taught by Ramanujan at very early age. This is one of his ability to think beyond the age, beyond the capability. That was one of Ramanujan's very beautiful idea. I could not go to the next slide. What should I do?
Sister. Ah, yes, sir.
Ah. So if you look at the notebooks of Srinivas Ramanujan, this is how it started. The first chapter, this is the original copy of the notebook. So blurred here because of some years dating. Nearly 139, 130 or 150 years since Ramanujan wrote this. So it was very damaged portion. Very little is visible. So this is a copy of the Xerox copy or something of the notebook. I will tell more about this notebooks later when I finish this talk. You see, two magic squares were drawn by Ramanujan in the first page. This is the first page of Ramanujan's mathematics. You see, two magic squares were drawn by him. The first magic square is a traditional magic square, what is called low shoe magic square, where 9 numbers are filled in 9 squares, 3 by 3 magic square, forming 15 in rows total, row wise, column wise, and diagonal wise, forming 15. And of course, this magic square, the first magic square by Ramanujan, getting 15 total, was known 2000 years ago. It's not new to people. So Ramanujan started with a traditional 3 by 3 magic square. And then the next magic square probably he did was with consecutive odd numbers. Like you see 1, 3, 5, 7, 9, 11, 13, 15, and 17. So this is the consecutive odd numbers, 9 consecutive odd numbers, forming 27 in row wise, column wise, and diagonal wise. So Ramanujan, being a mathematician of very deep nature, has started with this work with very nice recreational mathematics, not like magic. Magic was not serious mathematics, but it gives so much ideas and it makes people enjoy mathematics to a greater extent. Probably he could have chosen this, but I was thinking in my mind why Ramanujan of that caliber could have started his work by magic square. It took several years for me to understand it. So maybe I will share the answer later. And I was also thinking why the second magic square was constructed particularly. Probably because he was mixing religion with mathematics. He was so religious person, believe in God, and everything was given by God to him. And at many occasions, he used to say to his friends that any equation to me means nothing less than a thought of God, expression of thought of God. So he always believed that whatever he did, whatever greatness that he possessed, was due to goddess Namagiri Thayar, his family deity. And in that regard, the second magic square was formed with magic sum 27, which means probably that there are 27 stars in that we have. So probably he could have mixed that way. This is my guess, not probably known particularly. I'm not going to the next slides. I don't know why it's getting stuck.
So you stop share and again resume share, sir. If you have any problem, you stop share
Ah,
and resume share.
okay. It should come, isn't it? I mean, probably if I could go this way, I think it will come. So the other jottings of Ramanujan was this. Like you see, this is a very simple equation: 1 + 2 is 3, 2 + 3 is 5. When I showed this to young students, they were actually very happy because they could understand this equations very easily. They are not big deal to understand. So 3 + 7 is 10, 2 times 5. What Ramanujan was trying to do was forming equations with primes. In fact, they are consecutive primes. But one curious thing that you note among these equations was the first equation here, 1 + 2 is 3. When Ramanujan was very young, he could have written this. And you see, the first equation 1, if you claim that these are equations with prime number, then Ramanujan was thinking that 1 is prime. In fact, he did so in his young age. Several mathematicians had used 1 as prime number in earlier times. Only in recent times, in few centuries, we discarded 1 because of several problems that it comes to. So the first primes in modern times start with 2. But Ramanujan, when he was young, treated 1 as prime and he wrote all these equations. The other equations, of course, are correct. And this is also correct because if you treat 1 as prime. Okay? So he was probably young and didn't realize that you could not take 1 there. So the other thing that Ramanujan wrote was this. See, these equations are jottings of Ramanujan, written by Ramanujan and recorded in his notebook, original notebook. And this were his original handwriting. You see, this type of elementary patterns were formed not at the prime age. It was done at probably when he was studying elementary school, like third class or second class or fourth class or something, less than fifth class. Okay, that's very young age. So even at that ripe young age, he could see those patterns coming out beautifully. That is one of his wonderful things. You see, the equations have 1 by 4 in the first step and then added primes. 1 by 4 plus 2 is 1.5 square. 1 by 4 plus 2 times 3, this is 2 times 3, 2 times 3 times 5, so product of primes. And then he realized if you take 1 by 4 and add 2 times 3 times 5 times 7 times 11, you could not make it that the square, so the pattern gets broken down after the fourth equation. So, but he saw that when you multiply with 11, 13 and 17, you get a square. So he was master of observing patterns and making out beautiful equations. In this sense, I compare Ramanujan to painters like Da Vinci or Michelangelo, who create wonderful patterns in painting which became immortal today. And Ramanujan's mathematics is more or like such paintings. Yes. So the next slide here is about the enumeration of prime numbers by Ramanujan. This is the list of prime numbers that Ramanujan had made. This is not very clear to us. So to get a clear picture here, I will show the next slide, which is made by ourselves from the previous page. Whatever Ramanujan wrote, few rows are written here to have better understanding. So the first column here, you see, it has a special meaning: 0, 0, 1, 1. Leave away that now. So here Ramanujan, when he listed prime, maybe after a little more number of years than what he wrote here in this slide. Here I told you that Ramanujan could have considered 1 as prime in this very young age, but probably after some point of time, some number of years, he could have made this possible list and he discarded 1. So he probably realized that 1 is not treated as prime. So he started his listing of primes from 2 here. So 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. If you see, 97 is the last prime number before 100. And after 97, the next prime number is 101. So instead of writing 101, he could have written 1, 3, like this is 103, this is 107, this is 109, 113, 127, 131. So he could have left the first digit, the leading digit there, the 100th digit, and wrote the just two digits, namely the unit digit and tens digit. This is how he filled all these things. There are two reasons probably doing which made Ramanujan do this. One is that he didn't have uh, more economy to buy papers and write them elaborately column wise. If we could have done that, it consumes more space and more paper will be wasted. To save the space and use the ideas economically, you could have chosen this way. So this is one way of showing great idea with poorness. So Ramanujan was always blessed with two things. One is poorness, the other one is having great ideas. And this is one classic example of showing. So, what kind of creativity Ramanujan had? See, if you take the first number here, 71, 71 is a two-digit number, so the leading digit is 0. So, it continues up to 163 here. Then the next prime is 167, so the leading digit is 1, up to 199, then 211. Because it started at 1 here, he could not insert a 2 here, so he continued like that. So, this is 211. 211. This is 223, 227, 229, and so on up to 269. Then this comes here in 273, 277. Because it is 273, leading digit is 2 here, and continues up to 299. Then 307, 311, 330. See what beautiful way he could have enumerated. I hope that he could have listed nearly 5,000 primes here in the single page of his notebook. That is one of the beautiful things that Ramanujan did in this economical way. Okay, and other curious thing is that if you see, this is uh, after 397, the next prime is 401, 409 up to 499. So the whole set of prime numbers beginning with 4 ends up here. After 499, the next prime number is 503. So it started with 3. So there's no 4 here because all the prime numbers beginning with 4 is listed out here in this particular row. So he could have started with 5 here. So that is one of the thing. The other beautiful thing that you find here is he could have listed out uh, like filtering out numbers. He could have filtered the prime numbers of the form, say 4n plus 1, 4n minus 1, leaving away, because if you take 2 and 3, they are very special prime. They don't form pattern. So leaving away 2 and 3, he said that there are 166 primes between 4 and 1000. In fact, it is true that among first 1000 number, there are 168 primes. So if you discard 2 and 3, you have 166 as Ramanujan claimed correctly. So among those 166 primes between 4 and 1000, he said that there are 80 primes of the form 4n plus 1 and 86 primes of the form 4n minus 1. Similarly, the same number he got here when he changed the form from 4n plus 1 to 6n plus 1 and from 4n minus 1 to 6n minus 1. So he also saw that there are 80 prime numbers of the form 6n plus 1 and 86 prime numbers of the form 6n minus 1. He further subdivided this into other classes, like among this 80 primes of the form 4n plus 1, he saw that there are 37 primes of the form 8n plus 1 and 43 primes of the form 8n plus 5. So this 37 plus 43 constitute 80. And if you divide 4n minus 1 type primes, you get 43 primes of the form 8n plus 3 and 43 primes of the form 8n plus 7. So these two groups constitute this group, 4n minus 1 coming to 86 primes. So he is master of churning out numbers and listing out larger and larger numbers. One example is he wrote that there are 9592 primes up to 10 to the power of 5, which is 1 lakh. Up to 1 lakh, there are 9592 primes. In fact, it is correct. So all this, see here, it is 9 times 10 power, 3 times 10 power 8. this many primes. 4 times 10 power 6, it's very, so up to 10 power 8 this many primes, up to 2 times 10 power uh, 14 or so, 10 power 4, that is 20,000. There are 2,262 primes. So he could have written, gathered all primes and listed out how many primes does occur within that particular range beginning from 1. So this is one list about Ramanujan from his notebook. So why should we bother about only primes? What about the non-primes, which are composite numbers? In fact, he gave a list of long list of composite numbers. Like he said that there is no prime number between 23 to 29. So these are, there are, if you count numbers 24, 25, 26, 27, 28. This is the longest gap of 5 numbers between two prime numbers. That means if you take any two primes before 23 and 29, you don't get 5 consecutive composite numbers. This is the first instance of getting 5 consecutive composite numbers between two prime numbers. Similarly, the next larger gap of composites occur between 89 and 97. And the next larger gap occurs between 113 to 127, and so on and so forth. So this is about larger interval of composite numbers between two prime numbers. And this is a quite interesting list. When I showed the magic square in the first page, I told you about highly composite number. And this is the exhaustive list of highly composite numbers by Ramanujan. You see, this has a specific meaning. 2 is the smallest number with two devices. Maybe if I enlarge the screen, you can probably see. So 2 is the smallest number with two devices. 4 is the smallest number with three devices. 6 is the smallest number. These are number of devices, and this is the smallest number having that many devices. So 6 is the smallest device number with four devices. 12 is the smallest number with 6 devices. 24 is the smallest number with 8 devices. 36 is the smallest number with 9 devices. You find 24 and 36 there in the magic square. So they are highly composite numbers. Okay. And Ramanujan's paper, highly composite number, was very famous actually. And if you look at this, this equation here, 1 power 1 times 8 power 8 times 9 power 9 plus 3 power 3 times 3 power 3 times 12 power 12. It's easy to verify. Like factorize this 8 as 2 times 4 and factorize this 9 as 3 times 3. And the number of 2 that are occurring here will be equal to number of 2's here, and number of 3's that is occurring here will be equal to number of 3's here. You can easily verify. But what does that mean? One product is equal to another product. This is easy to write. Maybe students might write 6 into 6 is 9 into 4. There are many such occasions that you can write. So what great thing that you find in this equation. Each number is raised to the same digit. And not only that, not only they are equal in product, if you sum the numbers, like 1 plus 8 plus 9 is 18, 3 plus 3 plus 12 is 18. If you look at here, 1 plus 3 is 4, 4 plus 12 is 16, 16 plus 20 is 36. This is 5 plus 15 is 20, 20 plus 16 is 36. So they are not only equal product wise, but if you add the basic numbers, their sum is also equal. So this type of wonderful equations pops out at almost every page of Ramanujan, especially when he was very young. He was very fond of writing such equations which have more than one meaning attached to it, not just a simple equation. And this equation was one of his hallmark equation. He gave the condition that if alpha square plus alpha beta plus beta square is 3 lambda gamma square. If you choose alpha, beta, gamma, lambda, satisfying this condition, then he said that sum of these two cubes, so this is equal to, not printed clearly, this is equal to sum of these two cubes. So you could have guessed that upon choosing, this is one of the way that Ramanujan could have got that number 1729. If you choose alpha is 3, beta is 0, gamma is 1, and lambda is 3, then you see they satisfy this condition. Both sides become 3 on each side. Because beta is 0, alpha beta becomes 0, beta square becomes 0. When alpha is 3, you get alpha square is 9. And in the right hand side, you get 3 lambda. Lambda is 3 here, gamma is 1. So this is also 9. So 9 is equal to 9. So I have choose an alpha, beta, gamma, lambda to be this numbers. When you substitute here, you find that 12 cube plus 1 cube is 9 cube plus 10 cube, giving rise to the number 1729. So this is one thing that Ramanujan did. In fact, many people used to ask me how Ramanujan could have guessed immediately about when Hardy asked when he was in hospital in Putney in England. See, probably Ramanujan wrote about 1729 in at least three or four equations in his notebook. At least at four or five occasions, you find this type of identities where Ramanujan could have listed 1729. And if you write four or five times, it's easy for you to remember. There are some special numbers we always remember in our life. So it so happened that Hardy quoted a number which is already well known to Ramanujan, and therefore he pronounced that it is the smallest number with sum of two cubes in two different ways. So I think everything is decided predefinedly to make it immortal. God has decided that way. Now, the next thing that he wrote was if A by B is equal to C by D, then A plus B plus C power 4 plus, see this is a pattern here, A plus B plus C to the power 4 plus B plus C plus D to the power 4 plus you take this diagonal here, A minus D to the power 4 is equal to C plus D plus A. Come this way. We started with left to right, now come right to left. C plus D plus A to the power 4 plus D plus A plus B to the power 4 plus take this cross B minus C to the power 4. Now he wrote all those equations by choosing A, B, C, D satisfying this condition. He got so many equations here, and one of the equations here is also about 1729. This is another identity where Ramanujan wrote about fourth powers, not third powers, but sum of fourth powers. And curiously, he made a note here, small note. I don't know if it's visible to you. He wrote that 4 may be replaced by 2 also, which means the sum of this 3/4 powers is equal, sum of this 3/4 powers is equal even if you replace by squares. So if you replace this 4 each in each term here by square, still it works. That's one of characteristic of Ramanujan. So probably young students doing algebra, basic algebra, can take this as exercise problems and verify that they are true. This is one of very good exercise for young students. One of the most famous thing that Ramanujan was said about his mathematics was 1729. The other important thing that Ramanujan was very often referred was this calculation of nested root problems. So I don't want to spend more time in this. Just give a glance of, because it will take more time. The solutions are explained here. So he published this as question 289 in Journal of IMS. So he wrote three notebooks, contents in three notebooks, and most of his ideas that he wrote in three notebooks were published in Journal of Indian Mathematical Society, which was formed in the year 1907 by Ramaswamy Iyer. And Ramaswamy Iyer was very much interested in helping Ramanujan, so he volunteered to publish whatever Ramanujan wrote so that it might be visible to all other mathematicians throughout the country. In fact, more mathematicians, after Ramanujan kept publishing one by one in each issue, keep on growing their interest in solving puzzles by Ramanujan. In fact, what Ramanujan did was just like a magician. Like magician shows little by little. He start with a very simple trick and then extend his tricks one by one. And when he end the show, he will do the greatest possible trick that he has in his sleeve. So he don't reveal also whatever he did. He don't usually reveal. Just similar to that, what Ramanujan did was he never revealed what he had in his hand, what he thought in his mind. He always posed curious problems, and most interestingly, all those problems that were posed by Ramanujan were had the property that it clinched people towards solving them. It extracts interest in people in getting to solve the problem. You see a pattern here: 1, 2, 1, 3. The next term is 1, 4. So first terms in the nested roots are 1 each, and then second terms are 2, 3, 4 consecutive natural numbers. And in the next problem, it is 6, 7, 8, 9, the first term, and then you get 2, 3, 4, 5, 6, etc. So this type of hidden patterns were very often found in Ramanujan's mathematics. very surprisingly, see, after 3 issues only Ramanujan gave this answer. No one could solve this problem. So the editor then waited for 3 issues to see if someone could come out with the right answer to this questions posed by Ramanujan, but no one could possibly do. So people were asking the editor to publish answer for this, and Ramanujan gave the answers. He gave the first problem answer as 3. So it was very surprising, because you see, there are infinitely many square roots, the nested square roots. Even a single square root cannot be written as an integer, because if you take like square root of 3 or square root of 5 or square root of 6 or 7, if it's a non-square number, if it is not a square number, then square root of such a number cannot be written as an integer, because it becomes an irrational number. In such a case, how could on how could one believe that all this infinitely square roots will add up to a very nice answer like 3? This is very difficult to imagine even. I mean, leave about solving the problem. Even to think on the first case, the answer would be very nice as 3 or 4 like here. This is unimaginable. This is one beautiful thing that you find. Though the problem seems to be very complex, the method that which it is getting solved and the answer is very nice and very elegant. In fact, if you know this particular equation here, you could get the answer for the first thing. So you find n plus 3 as root of n plus 5. You cancel this n over here. You find n plus 3, the square root of n plus 5 plus n plus 1 plus n plus 6, n plus 2, and so on. So if you now go to the first slide that I showed you, probably, so this answer, this is n plus 5 plus n plus 1, this is n plus 6 plus n plus 2, n plus 7 plus n plus 3, so, and so on and so forth. So if you look at this step as how Ramanujan wrote, the answer for this nested square root problem, keeping in Ramanujan's notebook idea, should be 132. And I have chosen this particular equation because the answer that you get is 132 is because Ramanujan today is 132 years old. So this is what I guessed. So currently Ramanujan is 132 years old, if he could have been, because he was born in the year 1887. So a very nice equation popping out. And Ramanujan, as I told just some time back, was like a magician. He had this in his sleeve, a very general equation which forms the chapter 7 or 8, if I quote correctly, this chapter 8. If you see this equation here in this original notebook, you could have seen this equation, x plus n plus a. The equation is written for better clarity here. X plus n plus a is n times root of ax plus n plus a whole square, and so on and so forth. And if you substitute x is 2, n is 1, a is 0, you get 3, the first thing. If you substitute x is 2, n is 1, and a is 1, you get the second answer, the previous thing. So he never revealed this general formula to anyone. Even to the journal, he never revealed. It was known only later on. And this work about Ramanujan was, he wrote very little on geometry. He wrote many things on numbers and analysis, but he wrote very, very little on geometry. One of his that few work that he did on geometry was called squaring the circle problem, in which if you are given a circle, you want to construct a square whose area is equal to the area of the given circle. And this problem is not new to the Ramanujan's area, but it was known from the antiquity problem. It was one of the 3 classical problems of geometry, namely squaring the circle. Ramanujan was getting interested in solving the squaring the circle problem. So he gave a construction himself. So it takes some time, but he said that if you construct this uh, diagram, he said that the area of the circle drawn here will be equal to, approximately equal to, the area of the square drawn with the length RD here. So you see, this is R, this is D. So if you draw a square in whose side is of length RD, then that square will have an area approximately equal to this. In fact, he used for this, so this is how he wrote RD square, area of the square with side RD, area of the square with side A is A square. So he claimed with this construction, area of a square with side length RD square is area of the circle. This is what he claimed. And doing this for He used this approximation for pi, namely 355 by 113. This is very, very close to pi, and this was known to the early Chinese mathematicians also. This is close to pi up to 6 decimal places. Not exactly equal to pi, but very close to pi. With this error, this is the error portion, so very small. And he was master in computing pi values. So one of the page he devoted completely for writing. So e to the power pi times root of 22 is this much, e to the power pi times this much. So all these values are somehow related to pi. You see this ratio 17 plus 15 times root 5 by 17 times 15 times some expression here is divided by something here. 17 plus 15 times root 5 is 7 plus 15 times root 5 is 3.141592653. This is true up to this digit 53. So it's enormously accurate. So he gave many such nice formula. Like one of the formulas that Ramanujan wrote was take 2143 divide by 22 and take the fourth root. You get pi accurately to 6 decimal places. So this kind of very nice formulas were formed by Ramanujan. This is another page where Ramanujan wrote pi formulas. In fact, he devoted a special paper which I show you later for the because of the want of time. I'm just leaving that part. I'll just give a clue, and this is what I want to tell you. This is original page of Ramanujan. He could have claimed that 1 plus 2 plus 3 plus 4 and so on is minus 1 by 12. If you add this sum, you get minus 1 by 12. And people got very confused. He himself gave a reason for this. If you assume that this sum has values, for example, then multiplying by 4, you get 4c. See, if you multiply each term by 4, the first term will be 4, second term will be 8, third term will be 12, and so on. But he cleverly wrote in such a way that the first term 4 is written below the second term here. The second term 8 upon multiplying by 4 is written below the fourth term, the first series, and so on and so forth. So 12 will come here, 16 will come here, one term leaving after the other. So when you subtract these two equations, you get minus 3c in the left hand side. The right hand side, this 1 will remain as it is. 2 subtracted with 4 will give you minus 2. This 3 will remain as it is. 4 upon subtraction with 8 will give you minus 4, and so on. So this series here is known to mathematicians because 1 minus 2x plus 3x squared minus 4x cubed and so on and so forth. This has this sum 1 by 1 plus x the whole square. So if you compare this expression with this, you get this equation when you put x is 1, which is what Ramanujan did. So he substituted x as 1 here to get 1 by 1 plus 1 the whole square. That amounts to 1 by 4. So minus 3c becomes 1 by 4. So c is minus 1 by 12. And this is the reason that Ramanujan gave. And he also claimed that he has more methods, like to sum the values like 1 square plus 2 square and so on. You could multiply by 8. So the multiplying factors are powers of 2. Here he could have multiplied by 4, which is 2 square. Next step, he could have multiplied by 8, which is 2 cube. And as before, he could have written the answers below the second term, fourth term, leaving the odd number of terms here and subtract it. So if you subtract, you get minus 7c. This 1 square will remain as it is. 2 square minus 2 times 2 square is minus 2 square. 3 square will remain as it is. 4 square minus 2 times 4 square is minus 4 square. And you have this formula for this expression obtained here. If you substitute x is 1 here, you get 1 minus 1, that is 0. So Ramanujan concluded that 1 square plus 2 square plus 3 square up to so on is 0. In fact, what Ramanujan was trying to do, see, seeing simply this gives, this says that the answer is incorrect because the left hand side you have positive terms like 1, 4, 9, 16 and so on. How come summation of positive numbers becomes 0? Because if you add sum of positive number, the answer is finite or infinite, that is different. Anyway, you should get a positive number. Sum of positive terms can never be 0 or a negative term. But in the first case, you see sum of positive numbers adding up to 1 plus 2 plus 3 plus 4. Sum of all natural numbers adding up to infinity gives a negative answer. How come sum of positive numbers add up to a negative number? And how come sum of positive numbers adding up to 0? This got confused, and this is a prime reason why many mathematicians were reluctant to accept Ramanujan mathematics and give guidance to him when he was supposed to write his mathematics. approaching, seeking help with his letters to him. In fact, what Ramanujan was trying to do was connect these equations to what is called Riemann zeta function, which is, I'm not going much deeper because the heading itself says that it's glancing Ramanujan. So we just touch what Ramanujan did and go off. If you need any additional information or any details about this, you can write to me. So this is Riemann zeta function defined for a complex number s. This is 1 by 1 power s plus 1 by 2 to the power s plus and so on and so forth. This was a generalization of what is called Euler's zeta function, which holds true only for real numbers, but Riemann extended that to complex number. Now, if you put ss minus 1 here, you get this. And people now, so according to Ramanujan summation, this is minus 1 by 12. And zeta of minus 2 is 0 because we just derived above. So these two results. So what Ramanujan was actually trying to do was to arrive a special summation method today known as
கொஸ்டினே
name
வரல.
called
ஏதாவது ஒரு கொஸ்டின் எழுதுனேன்.
Ramanujan summation method. So this is the equation portraying Ramanujan summation method, these two equations. So if you add sum of um, I'm like 1 plus 1 to the power 2k, this is even powers. So if you add even powers to natural numbers, you get 0. If you add odd powers to the natural numbers and so on, you get minus b2k by 2k, where b2k is the 2k Bernoulli numbers which are listed out here. And Ramanujan is very fond of Bernoulli numbers. In fact, his first important research paper was properties of Bernoulli numbers, some properties of Bernoulli numbers, which I'll show later. So he was very well versed in Bernoulli numbers, and he used those Bernoulli numbers as tools to evaluate what is called Ramanujan summation. So that is the this is the reason why he wrote all these equations. And when he sent his letters, he could have written, under my theory, I found that 1 plus 2 plus 3 plus 4 is minus 1 by 12. 1 square plus 2 square plus 3 square is plus 4 square is 0. But no, he never revealed what theory that he was proposing and what theory that he was doing in his mind. So because these equations were written by him separately, and in the letters he just wrote these answers, which are byproduct of this equation. These are special cases of this equation. He could have never revealed anything that he was concerning about Riemann zeta function, or doing his own summation method or something like that. So people got literally confused about what Ramanujan was writing up, and therefore they were quite reluctant to accept what Ramanujan did. This is the reason. The other important work by Ramanujan was to get partitions, for which he was awarded FRS. Of course, I will give those things also. So if you take number one can be written in only one way as one. So number of partitions of one is one. Two can be written in two ways, namely 2 as well as 1 plus 1. So number of partitions of 2 is 2. If you take 3, you can write 3 as 3, or 2 plus 1, or 1 plus 1 plus 1. So the partitions of 3 is 3. If you take 4, you can write 4 as 4 simply, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 added 4 times. So the partitions of 4, number of partitions of 4 is 5, because 1, 2, 3, 4, and 5. There are 5 ways you can split 4. So that, see, in doing this, you seek order. Like if you write 3 plus 1, you can't take 1 plus 3, because 3 plus 1, the commutative property is same as 1 plus 3. So that is not different to it. So this type of thing. There's another way of splitting called compositions. Compositions is literally splitting the number where 3 plus 1 is different from 1 plus 3. So and in fact, it is easy to see that for a natural number n, the number of compositions is 2 to the power n minus 1. You get 2 power n minus 1 compositions for a number n. But what made people like Euler and Ramanujan to think more was there is no explicit formula for finding number of partitions for a number n, until Ramanujan succeeded, along with the help of Hardy and Littlewood, in showing that the partition of a number n is approximately, whenever n is very large, is equal to 1 by, of course, this expression was not exactly the one obtained by Hardy and Ramanujan. That is quite complicated. This was simplified to the simple form by Rademacher, the other mathematician who came little later. The very simple form of partition formula, where this number k is given by pi times square root of 2/3. And Ramanujan was also, but see, as I told you, partition theory existed before Ramanujan. It was not originated from Ramanujan. It was known 1.5 centuries before Ramanujan's time itself. Euler did great work in partition in forming identities, but Ramanujan Ramanujan's two main contributions was to find the explicit formula for partition whenever n is very large, what we call asymptotic formula. The other one is forming congruence for partition, that is congruence partitions identities for Ramanujan. That is the first thing that people came to know. So Ramanujan's original contribution in partition theory was finding an explicit formula as well as forming this congruence among partition values. No one before him did this. So what Ramanujan did, I will to explain this equations here. I will just go to the next slide. But you see again a pattern emerging out here. Partition of the numbers of the form phi n plus 4 is a multiple of phi. It means they're always divisible by phi. If you take partition of numbers of the form phi n plus 4, they are answers which are divisible by phi. Partition of the numbers of the form 7n plus pi is divisible by 7. You see, this answers here 5, 7, 11 are simply coefficients of n here. And those are prime numbers 5, 7, 11. They are consecutive primes. And these are consecutive numbers like 4, 5, 6. They are consecutive natural numbers. So 4 is 1 less than 5, 5 is 2 less than 7, and 6 is 5 less than 11. 1, 2, 5 is the difference here. And then Ramanujan proceeded with other congruence identities, like he squared this 5 and got 25 here. If you reduce 1 to 25, you get 24. This 4 is 1 less than 5, 24 is 1 less than 25. He found again that this answer is divisible by 5 square, which is 25. If this is divisible by coefficient of n, namely 5, this is also divisible by coefficient of n, namely 25. Similarly, if you square this 7 here, you get 49n. This 5 is 2 less than 7. This 47 is 2 less than 49. So this is multiple of 49. So 121, the square of 11. So keeping this as basic entities to generate new entities like this. And this was first done by Ramanujan. Of course, he was wrong in one or two equations, which was proved by Chawla later, that some of the conjectures that Ramanujan made like this turns out to be false in partitions. So not everything Ramanujan did happened to be true. So I was wondering how much true expression that Ramanujan wrote and how many went false in his total mathematics. I saw that nearly 4 to 5% of whole of Ramanujan mathematics went
Feedback போதா பாரு.
wrong, but the rest 95% was correct, which is quite acceptable. I mean, very great. In fact, considering the fact that Ramanujan never went to university, he was a self-tutored genius. So, learning himself and keeping the ideas through his own way, uh, producing formulas to 95% accuracy is enormously good. So keeping that way, we should really admire Ramanujan. Now, if you take 4, the answer is 5. Partition of 4 is 5, as I told earlier. And if you take 9, this is 30. Partition of 9 is 30, you see. Partition of 14 is 135. So this numbers 5, 30, 135, partition of 19 is 490. This numbers either end in 5 or 0, and such numbers are clearly divisible by 5. This is what Ramanujan tried to say here. So the number that I told you here, 4, 9, 14, 19, 24, 29. So if you look at those answers, they're always answers, partition of values, which are divisible by 5. Similarly, if you take partition of 7, namely um, partition of 12, or partition of 5 is starting with 5 here, partition of 5 is 7, then add 7 to it, you get 12. So first value for 5 is 7, that is divisible by 7. Partition of 12 is 77, that is divisible by 7. Partition of 90 is 490, that is divisible by 7. Partition of 26 is 2436, that is divisible by 7, as you can check. Partition of 36 is divisible by 7, 17977. So if you keep on adding 7 to the values beginning with 5, you always get an answer divisible by 7. That is what Ramanujan was trying to say from this partition identity, congruence identity. So this type of, and this table was compiled by Ramanujan himself. So you see the partition of the number 100 is 190569292. It's hugely, so as n grows, partition values goes very large. And this equation here is x power x square plus 7 is 2 power n. So So if you want to list out the integer values of x and n, you get 1, 3, 3, 4. First coordinate is for the x value, second is for n. You can verify that this 5 solutions will satisfy the equation x square plus 7 is equal to 2 power n. Now what Ramanujan did was he not only listed out these 5 solutions, and he claimed that these are the only 5 solutions in integers. You can believe that it took more than 3 decades to get this proved. Finally, it was proved by French mathematician Nagel in around 1948 or 49, long after Ramanujan passed away. So a simple observation that there are only 5 solutions to looking very obviously very simple equation had kept mathematicians busy in proving it for more than 3 decades. That is the depth in Ramanujan's idea. So one of the big things that you find. So the observations are quite easy to make, but getting it proved is very hard. And this is the very famous Roger Ramanujan identities. You get, see, I wrote these identities particularly because to get see how beautifully Ramanujan's mind is embedded with patterns. This is q power 0, q power 1, q power 4, q power 9. So you get square numbers here, q power 1, q power 4, q power 9. The powers of q are what is called the square numbers, and the denominator you get 1 factor, 2 factors, 3 factors here, which is of the form 1 minus q, 1 minus q square. And if you see here, if it ends with 2 here, this is 2 square. If it ends with 3, this is 3 square. So this is how Ramanujan formed here. And this numbers here again forms a wonderful pattern. If you take this power here in the first factor, 1, this power is 4, the next power uh, is 7, the next term it is 7. So they are arithmetic numbers in arithmetic progression with 3 common different. This is 6, 9, the next term it is 12, again numbers in arithmetic progression, 11, uh, 14, then the 17 the next power. So similarly, the next thing is also here, this is product of 2 consecutive natural numbers, like 1 into 2 is 2, 2 into 3 is 6, 3 into 4 is 12, and such numbers are called oblong numbers or rectangular numbers, whatever it is. So the first equation, the powers are square numbers. The second equation is oblong numbers or rectangular numbers, and same pattern continues here. But this powers are different. You see 2, 3. The next term is 4. Here it is 7, 8, 9. The next term 12, 13, 14. So you get obviously some embedded pattern here, and that forms wonderful thing. And I also observed that if you look at this powers here, 2 plus 17 is 19, 7 plus 12 is 19. So they also become equal to each other. And the other great contribution by Ramanujan was introducing what is called tau function, which is an arithmetic function in number theory. And tau function, tau of n, is a multiplicative function, meaning that if you choose two numbers mn co-prime to each other, then you can show that tau of nm is tau m into tau n. That is simple, like in algebra, we prove that a function phi is a homomorphism if phi of ab is phi of a into phi of b. Similar to that, we call such functions as arithmetic functions here. But this holds true if you choose two numbers mn whose GCD is 1. And he also showed that conjecture the tau of p power r plus 1 is this equation for all prime p. And this is called tau conjecture. Tau of prime number p is less than or equal to 2 times p to the power 11 by 2. And he also conjecture the tau of pn is congruent to 0 mod p only for this prime numbers. Only for primes which are 2, 3, 5, 7, 23, and 691. For this 6 prime numbers. See, it took several years for mathematicians to prove this. In particular, this inequality, mod tau p is less than or equal to 2 to the power 2 times p to the power 11 by 2 for all primes p, was proved by French mathematician Pierre Delling around 1974 or 75, for which he was awarded Fields Medal, the greatest prize in mathematics. This is the great thing about Ramanujan. See, many mathematicians got inspired by the work of Ramanujan, and they started working in their own way. And even if you prove one or two equations in Ramanujan's mathematics, you become world famous. So Piri Delling and Manjul Bhargava and those people got inspired. Even Paul Erdős got inspired by Ramanujan's mathematics, and they became very great people in their own way. So these are the areas that Ramanujan doing in his lifetime. 11 areas that you can classify: elementary mathematics, number theory, infinite series, asymptotic expansion and approximations, integrals, hypergeometric functions, continued fractions, Q series. See, this Q series is one of the things. This is called Q series. This is an example of a Q series. Q series, theta functions and modular equation. This are the work that theta functions were the work which was done during his death time. Ramanujan's last work was theta functions, elliptic functions to alternative basis, and class invariance. So this idea of class invariance have beautiful connections with what is called K3 surfaces, and it is used very widely in differential geometry currently. So, though the Ramanujans primarily worked on number theory, his ideas were used very vastly in other areas, even areas related to what is called atomic number theory. In particularly, if you look at this particular equation that Ramanujan proved, 1 plus 2 plus 3, which is zeta function at the value minus 1, which is minus 1 by 12, it was guessed by mathematicians like physicists like Freeman Dyson and who recently passed away, and other people, that it was used in string theory, and now they uh, see this is application in calculating the entropy from the radiation of a black hole. So, so many things are getting applied quite unexpectedly. I'm sure Ramanujan himself would not have guessed even to the smallest way that his formulas could one day get applied in finding entropy values for a black hole radiation, or getting applied to explaining string theory, or getting applied to various other practical engineering forms. So these are my famous equations found in Ramanujan's area. My classic thing. This is one of the beautiful formula that Ramanujan wrote for pi, which printed pi to 17.5 million digits accuracy. So this is infinite series, and this is continued fraction expansion. If you see ones coming out here, and this ones are consecutive natural numbers. These are infinite series. So infinite series add up to a continued fraction, simple continued fraction. Answer turns out to be a term which is square root of pi e by 2. Pi and e are two most important real numbers. No one could guess that this would add up to this number unless Ramanujan revealed them itself. So this constant 0.764223 is called Ramanujan-Landu constant or Landu-Ramanujan constant. You see, this is the formula that Ramanujan gave, but he had a general formula which I show you here. This is general formula that Ramanujan had in his mind. So, keeping general formulas, he could substitute particular values and generate many special cases. And this is infinite product equation where you could have taken prime numbers 2 square, pi, 3 square, pi square, 7 square. So product of prime squares plus 1 divided by product of prime square minus 1. He proved that is something like that. And this equation is another summation formula. These are not so difficult, but with some effort you can prove this. And this is another equation where he connects integral with the continued fraction. And you can understand this our special formula that we do in our classrooms in BSc class. Like if you take a is infinity in particular, then e power minus a square becomes 0, because e power minus infinity is 0. So this whole terms become 0. So if you take a is infinity, you get 0 to infinity e power minus x squared dx is root pi by 2. That is what we do in beta gamma integrals, as well as in integral formulas. We can do this by multiple integrals also, which we do in first year calculus problems for students in our class. But what Ramanujan did was taking, instead of infinity, he took a finite number a. If you took a finite number a, the answer is root pi by 2 subtracted with this term. So that was he was obtaining as a continued fraction. And he gave a summation formula for computing what is called Euler-Mascheroni constant, what we call gamma. So he was working with all kind of things. He wrote a formula with golden ratio here, one of beautiful formulas treated as these formulas are considered as gems by many mathematicians working under his mathematical view. So these are my favorite formulas. Everyone has their own preferences. So this equation has a big story. I don't know how much time I'm left with. So I just give a glimpse of when Ramanujan was asked to find solution for this equation. This was said through a story, but I'm leaving the story for the time purpose. He gave this answer. The solution for this equation is this answer. continued fraction 3 1 by 6 1 by 6 1 by 6. If you churn out the first few terms here, 3 1 by 6, you get 19 by 6, and this forms the first part of the answer here, because we put x is um, this is the denominator is x and numerator is y. So if you put x is 6 here, you get 6 square is 36. 10 times 6, 36 is 360. The numerator is y. So if you put that here, 19 square is 361. 360 minus 361 is minus 1. And if you take the next term, this is 3 1 by 6, the first term. If you take up to this term, 3 1 by 6 1 by 6, up to second term, you get 117 by 37. You substitute this here, x, substitute 37 for x and 117 for y. 37 square is 1189 or something. Yes, 1189 or something like that you get, I don't remember. So you multiply that by 3 and square 117, the difference will be 1. So if you plug the first solution, you get minus 1. If you plug the second solution by keeping out this, you get plus 1. If you take the next part, you get minus 1. If you take the next part, you get plus 1. So not only Ramanujan solved this equation, but he gave infinitely many answers. The answer was in terms of a continued fraction. This is one way that its mind work enormously well compared to normal people like us, where we even struggle to find a single solution to a problem or to an equation. So these are one of classic formulas that Ramanujan wrote in his notebooks. And some of those formulas, Hardy said, was excellent. He had himself not seen like this before, anything like this before. So he could have told that defeated me completely. See, Hardy was not an ordinary mathematician. He was a great mathematician at England. When he said that I have not seen like anything like this before, and this formulas are very new and entertaining, and he honestly said that this formula defeated me completely. That was one of the great thing that even Hardy admired Ramanujan for his wonderful formulas, and Hardy considered it sufficiently marvelous that he could have even dreamt of problems of such as this. He could not have even guessed this. So these are applications, some of the things that came out as Ramanujan's thing. Study of asymptotic behavior of partition formula led Ramanujan and Hardy develop circle method. This circle method was developed by Hardy, Littlewood, Rademacher. I told Rademacher in refining the partition formula, Vinogradov, Davenport, and other mathematicians. And those methods were helping people to solve this very, very important unsolved problems of previous centuries, like log-sieve method, ternary Goldbach conjecture, progress on binary Goldbach conjecture, and Waring's problem. So all this problem look beyond the reach before the birth of circle method. So Ramanujan's formulas are not only good and great, but it also paved way for solving this very, very important problems in mathematics. So I leave this Waring's problem, you can look at it. Waring conjectured this, and this was solved by using Ramanujan's idea, SS Pillai, the other great mathematician, using the circle method, solve Waring's problem for all values of k from 6 to 100 and beyond 100 with certain conditions. So Ramanujan method became a base for SS Pillai to solve Waring's problem, and eventually SS Pillai was considered next to Ramanujan. After proving this Waring's conjecture, his name got so famous in mathematical circle. Ramanujan's classic paper in the form ax square plus by square plus cz square plus dt square, which is quadratic form, was instrumental in generating interest among many young budding mathematicians even today. In fact, one of such mathematicians was Manjul Bhargava. He said in many interviews that this paper by Ramanujan was the first thing that he got interested in doing higher mathematics. Eventually, he proved what is called a 290 theorem, which is concerned with expressing any natural number in terms of quadratic form like this. So with his collaborators, he could prove that any number, any natural number can be written by using at most 290 quadratic form. That is called 290 theorem. You can go and check later, for which he was awarded Sasa Ramanujan Prize. And Manjul Bhargava eventually won the Fields Medal in the year 2014 also. And whenever Manjul Bhargava gave any interview, he always acknowledged Ramanujan for keeping the spirit and getting interest as a young man in him. So this was some of the advantages of Ramanujan's mathematics. You can so some contributions of Ramanujan was introducing probabilistic number theory originated from his work. almost all numbers have log of log and prime factors. Roger Ramanujan identities, which I showed you, mock theta functions, and many mathematicians, including say Anand Rao, who was contemporary to Ramanujan, or Vaidyanatha Swami, who was at Madras University earlier. S.S. Pillai, I told you. T. Vijayaraghavan, who was also along with Ramanujan's period. In fact, this T. Vijayaraghavan found an error in Ramanujan's work in highly composite numbers, not an error, but a slipping. Like Ramanujan could have left one entry, T. Vijayaraghavan found that entry and filled the gap. So he became famous for filling that gap. Chawla was the one I told you he was very famous, and he disproved one of the partition congruence identity of Ramanujan. Harish Chandra, with whom Harishchandra Institute Allahabad is named now. He's a very great mathematician. C.P. Ramanujan, V.K. Patodi, Chandrasekhar, this were stalwarts in Indian mathematicians. Of course, P.K. Srinivasan, my mentor, who was instrumental in bringing Ramanujan to common people. So these people got inspired more by Ramanujan. Eventually, they became famous by themselves. So these are some of the applications. Ramanujan's work has some application, particle physics, computing pi to a very, very large number. And Ramanujan formulas apply in statistical mechanics. The work on Riemann zeta function has applications to pyrometry, that is the investigation of the temperature of furnaces. And the work on partition of N has applications in new fuels and fabrics like nylon. And Mach theta functions, as I told you, has this is the recent discovery. They help theoretical physicists to understand string theory and black holes and all those things. These are the papers published by Ramanujan. The first paper, important paper, published paper, was some properties of Bernoulli numbers, and most of them were published in Indian Mathematical Society, as you see, and most of them were published from the year beginning from 1911 until 1999. Sorry, 1990. This 9-year period. I'm sorry for that. 1911 to 1919. This 9-year period were the glorious years for Ramanujan, because those were the period when all Ramanujan's work got published officially, and his work got circulated among world mathematicians and became very famous eventually. You see, this is a complete list of what Ramanujan published, and all this papers and details about them were given in the book Collected Works of Ramanujan, edited by Hardy and Seshwariya in the year 1927. The book is still available. So Ramanujan wrote 30 papers on his own in his lifetime. This was all the 30 papers were written by him. Each one of them is a classic paper and a gem, considered as a gem. This was the paper that inspired Manjul Bhargava. I told you, certain expression of a number in the form, quadratic form, ax square plus by square plus cz square plus du square, quadratic form. There's several other things that Ramanujan, and this Euler's constant gamma is a formula that I showed you earlier, which Ramanujan did. And the 7 papers by Ramanujan were in collaboration with G.H. Hardy, his mentor, his close friend. See, I could say at this point of time that without Hardy, Ramanujan could have not known as he is today. So we owe a lot as Indians to Hardy for bringing out Ramanujan's talent, bringing out Ramanujan as a man, as a mathematician to the world, and express his ideas completely. So that's why we always cherish Ramanujan along with Hardy when conduct a function. These 3 notebooks are the one that were kept in Madras University as a remembrance of Ramanujan. All those basic formulas that I showed you were kept in this notebook, were jotted in this notebook. These notebooks were scanned and reprinted by taking in new technology. They were revised, and it was published in the year 2012, during the 175th birth anniversary of Srinivas Ramanujan. It was published by Tata Institute of Fundamental Research, TFR, and the Chennai press here. I don't remember the press name. It was in Mylapore or somewhere. They published all these books on behalf of TFR. In fact, TFR gave those books at a very nominal rate for Indian citizens. For foreign authors, it is quite expensive. So I got some copies of that. And this is the last notebook which was discovered by George Andrews in the year 1976 when he was searching for manuscripts of Ramanujan. There's a big story about this lost notebook. The recent research about Ramanujan and Mach theta functions identities were kept in this last notebook. People are working on that book now, and these 2 people were the great men who who have spent more than 4 decades of their life in working out Ramanujan's formulas and proving one by one. They were devoting their whole life for Ramanujan's work. And this is the key photo of Ramanujan. Ramanujan is still standing at the center here during offering BA degree, what is called BA by research. I will talk about this. Is FRS certificate given to Ramanujan, the copy of the original certificate. So Hardy is the first proposer of for Ramanujan. The other mathematicians could have signed out here in support of this nomination. And Ramanujan today was known for this idea: Ramanujan graph, Ramanujan summation, theta function, Ramanujan Nagel equation. That is the equation that I showed you: x square plus 7 is 2 power 7, 2 power n. Ramanujan's congruence, Landu Ramanujan constant, which I showed you. Some of them I showed you, but some of them could not. This Ramanujan's master theorem is one of classic theorem. Unfortunately, could not write. And there are primes known as Ramanujan prime. When he did Bertrand's postulate, he introduced this idea of what is called Ramanujan's prime. Tau function I showed you. So some of them I showed you. Roger Ramanujan entities I showed you. So this is the original slate by Ramanujan. I had a very great opportunity to hold that in my hand. In fact, Bruce Byrne was also holding that particular slate some years back. And this is the photo of Sri Narayanan, who was adopted son to Ramanujan. I am holding the original passport that Ramanujan came from England. He took this original passport when he returned from England in the year 1990. I was also happy to be part of two films. There were two films that were made on Ramanujan. One is Tamil film, same name Ramanujan, released in the year 1914. The other one was released in the 2014. In 2015, an English film in the name The Man Who Knew Infinity was released by Hollywood, in which many mathematicians like Ken Ono, Bhargava, Manjul Bhargava as part of the team. It was a very good film, Man Who Knew Infinity. Tamil film was also very good in the sense that it concentrated more on life part, whereas the English film concentrated more on mathematical part. And my little help in for the film crew was acknowledged by showing my name here in the beginning screening of the film. Now I wrote this in the Pi Association website on the date, say you see, 24th of December 2019, during the Ramanujan birthday celebration, which is on 22nd December. So I could not post this on that particular date, but during that occasion I posted this. I was saying in that recently we were getting so many false news about Ramanujan, so many false pictures circulated about him. So before I close this talk, I want to just say a few things and then close my talk. Recent message about saying that Ramanujan was great because of the numbers 220 and 284. If you add divisors of 220 excluding 220, you get 284. And if you add divisors of 284 excluding 284, you get 220. They resemble each other. That is why Ramanujan was considered to be great. In fact, this mathematical fact, was discovered by Pythagoras some 2,500 years ago. This is the first least amicable pair and not attributed to Ramanujan. See, Ramanujan contributed totally 3,872 theorems and formulas. There are plenty of reasons, more than 3,000 reasons to celebrate Ramanujan in a true sense. Someone's contribution and celebrating. People in other branches like history or Tamil or language, people can claim this way, then it is no harm in it. But we mathematic people, if we claim false like this, then I think it is very bad on our part. Because Ramanujan did so many great things in his life. There are so many great reasons for celebrating his mathematics, but leaving all those things, and if you attribute
only 5 minutes more
to celebrate Ramanujan, we should avoid that. So whenever you I'm finished, madam.
Okay.
So whenever we see such thing, madam, I want to just see some of the important things, so please just
okay sir, no problem, continue. Just time crossed.
I'll finish as quickly.
Okay sir, you continue, sir.
So this is like 220 and 284. If you see WhatsApp message, please inform everyone that it is a mistake. It is my humble request to every one of you. And the other message that is often circulating in WhatsApp, see the symmetry in this equation. This is why Ramanujan is best Ramanujan wrote this kind of simple and very trivial equation were more than a cakewalk to Ramanujan. He could have never guessed this. This is very simple for Ramanujan. For such his caliber, these equations should not be attributed to him. This can be thought by every one of us. So Ramanujan is much capable than this. Writing this, it was not done by Ramanujan. Please note that. And there was some magic square which is attributed to Ramanujan. You see this link here. Go to this YouTube link. This link has been seen by nearly 1 lakh people. There's another link which is seen by nearly 5 lakh people about Ramanujan. And there are so many properties like adding this way, that way, so many ways. As I told before my first screen, that you get 139 total. But the first row contain Ramanujan data, but it can be constructed by anyone, as I did yesterday. So this, Ramanujan never constructed this magic square, but you claim in the video, it claims that many people claim that it was constructed by great mathematician Ramanujan. It was not constructed by Ramanujan. No data but square was constructed by Ramanujan, because I have the original notebooks with me. I can show to you. So this is a mistake that we do. The other mistake that I will quickly glance through this recent video about Ramanujan. This saying that this is a very famous video actually circulated during Ramanujan celebration time almost every year. This was Srinivasa Varadan, not Srinivasa Ramanujan. Srinivasa Varadan got admired by Ramanujan, and he himself became an Abel Prize winner very recently in 2007, if I remember. So he was himself a very great mathematician, very simple man. He studied at Presidency College, Chennai, and he went to US and did great work. He said in many interviews that my motivation was Ramanujan, and he himself was from Kumbakonam, where Ramanujan lived. So, but unfortunately, his photograph was taken for Ramanujan. That is not correct. So, showing this photo, many people say that it is Ramanujan. In fact, it was published by an important paper, as you all know. So many news were circulating upon this. It is quite incorrect. And in this video by News 7 channel, which was published 3 years ago during 2 years ago during birthday celebration, it was said that this was Ramanujan's father, mother, and there's no photograph of his father. Truly speaking, only Ramanujan's mother's photo was available. No photo of his father existed so far. I don't know who's this man, but later on I found from some other people that this was S.R. Ranganathan, who was a contemporary to Ramanujan, was first librarian at Madras University. He was called father of library science in Madras college now. So in library science, he was a king among all people. He is the one who included the column norming and other things in basic aspects of library science. And this lady was wife of S.R. Ranganathan. So some false claims that were circulating, and this man was A.K. Ramanujan, who was a poet, English poet, and his wife. But people often claim that this was Ramanujan along with his wife Janaki Ammal, which is quite not true. And many people say that Ramanujan never scored less than 100 in mathematics. That is unfortunately not true. This is a FA mark sheet of Ramanujan, in which Ramanujan could have scored only 85 out of 150. These two papers, physiology and history, he never appeared. So it is not true that Ramanujan always scored 100. Ramanujan was very good at mathematics. He never bothered about marks. This is true. And one man, when he was giving a talk, used to ask me, several people at several instances used to ask me, this Ramanujan can be called as doctor because he was not assigned a PhD degree formally. I was only smiling at them, because today, even if you produce one particular result, you are called doctor. Ramanujan could have written original theorems which amounts to nearly 4,000.
See, your voice is not audible, sir.
So at least leaving away 5 to 10% of known results by other mathematicians, 400 that were attributed to Ramanujan. So even if you could give one PhD for one of his results, you could easily assign more than 3,000 PhDs to Ramanujan. But in fact, Cambridge University was acknowledging this by Ramanujan. I showed a previous photograph for his work on highly composite numbers. He was given BA degree by research. In fact, Cambridge University recently, some years back, announced that anyone before 1920 was awarded BS degree by research is eligible for doctorate. So they can be awarded as PhD. So even in that sense, Ramanujan is easily in PhD. This is where Ramanujan is born. I wrote this article. This is at Erode about published in Hindu. So if you go to Google and type, this is where place of Ramanujan, which was not known to many some years back. It was only known some 8 or 9 years ago, not known to many. These are the books that were very good on Ramanujan mathematics. Ramanujan's notebooks. There are 5 parts here. For the want of space, I just took one part. There are 5 parts in Ramanujan's notebooks, which contains the proof showing you. And there are again 5 parts in Ramanujan's last notebook. And this is a very elementary book written by Bruce Bunn. So those who want to see the actual proofs of Ramanujan, including the partition, congruence, identities, you can refer this book written by Bruce Bunn, Number Theory in the Spirit of Ramanujan. This book by Ramurthy goes beyond the Ramanujan notebooks. It's a very deep book written by Ramurthy and Kumar Murthy's brother, The Mathematical Legacy of Srinivasa Ramanujan, a very good book. And this was written by Krishnaswamy Alladi, named Ramanujan's Place in the World of Mathematics. So, and this is the collector's edition introduced in the year 2012, as I told some time back, released by TFR, which is a scanned version of Ramanujan's original notebooks. The papers are of very high quality here. So long as our planet continues to exist in the universe, this is by Chandrasekhar said about Ramanujan. So I feel that as long as people do mathematics, they will always remember Ramanujan. And he was a mathematician who, in spite of poverty, did great research in mathematics. He always spent his whole life for the sake of mathematics. So with this, I thank everyone for giving this wonderful opportunity, particularly Ramurthy sir and Nalini madam and other colleagues in Theagaraya College, because their names are not known to me, so pardon me for not mentioning. And other participants and teacher friends who are, I hope you got something at least from this attending this webinar. And if you have any special particular doubts, you can write to me. My mail ID is easily available with them, and contact the organizers to get them. I'd be happy to help you. I got myself personally admired by Ramanujan to a larger extent. I always pray him, and I take this as a wonderful opportunity and tribute to him to participate in this webinar and share what little I know about him.
So
and I tribute this webinar.
Question session is there, sir.
Centenary year of Rama. Okay.
So shall I pass on to the question?
I would be happy to answer.
Question session. I shall pass on to the Shuganti ma'am. She will ask. Hello. Hello.
Yes. Tell me. Please,
hello.
If there are questions, please ask.
Hello, Shanti.
Hello.
Hello.
Shuganti.
Yes.
Shuganti ma'am, please raise the question.
It's audible. Please ask me.
Sir, one of the participants have asked, what made you so fascinating to do analysis, especially so deep in Ramanujan's work when so many topics are there? Hello? Hello, am I audible?
Hello.
Hello,
Tell me again,
Any
Shuganti.
questions?
Yes, yes.
Hi, so one of the participants have asked, what made you so fascinating to do the analysis, particularly so deep in Ramanujan's work?
Madam,
when
I
so
could not
many topics.
hear you. Please, can it be audible? Or someone could share the question.
Am I audible, sir?
Sir, what
Yes,
made
yes.
you fascinating to do analysis, particular in Ramanujan's work when so many are there?
So many of this. See, I have more interest upon him right from a young age, but when I became close to a man who I mentioned in my presentation, namely P.K. Srinivasan, he was a man who lived his whole life for collecting Ramanujan's manuscripts and other details, and he did all those things in a very grand manner. And I'm very fortunate to be with him for at least few number of years. And in collaboration with him, I came to know all those things. He was a man who brought out Ramanujan to people like me.
Thank you, sir.
Hello.
Next
Okay.
question.
Okay.
Next
Close the
question.
session.
Some of the students have asked questions like, is there any books or websites that they can refer for Ramanujan's work?
Can you repeat the question? I could not hear the
No, sir.
question.
Students have also registered. They wanted to know, is there any websites or books so that they can regarding the Ramanujan's work, so that they
The
can use
books
it.
that I showed were all from foreign publications. They are not available even in PDF form or any form from the net. So I
Okay.
had purchased on my own cost. I mean, I ordered them specially with special agents who can possibly get you this by imported books. I think you can even order them by Amazon or some other thing. I don't know about today's condition because most of the books and products were not deliverable by Amazon because of this pandemic condition. But I hope in future you can order them and get. But I'm very much sure that it would cost more number of money. But even the time when I bought this around 15 or 17 years ago, it was costing me around several thousands of rupees. So now I hope it could be costing much more than those times. It's quite costly, but if you can afford, it's worth getting.
Okay. Okay. Thank you, sir.
Thank you, sir. Now I request Shanti ma'am to propose the vote of thanks.
Good afternoon to all. On behalf of the Department of Mathematics, Theagaraya College, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this webinar on glancing Ramanujan's mathematics. At the outset, I thank our speaker, Professor Dr. R. Sivaraman, for his excellent presentation. We are really enlightened with your knowledge and lecture. Thank you, sir, for your very interesting address, and we are very blessed to see the jottings of Ramanujan. We are thankful to our Honorable Secretary and management members for their motivation. I would like to thank our principal, Dr. P. Senthilkumar, for providing encouragement and support. A special thanks to our HOD, Dr. Ramamurthy, for his moral support, and my colleagues, Dr. Nalini Devi, who is the convener of this webinar, and Dr. Shuganti. Our heartfelt thanks to all the participants for their active participation. With these warm words, we move to the end of today's webinar. Thank you.
Thank you, everyone.
Once again, I thank you everyone for making this webinar a grand success. Participants, please fill up the feedback link so that your certificates will be sent to you through your email. Thank you so much. Last but not the least,
Welcome, sir. Thank you very much.
let me end the webinar with national anthem. Please rise.
So should we stand then?
Yes. Yes, sir. Once again.
Sir, ಏನು ನಿಂಕಣಮ್ಮ?
Once again.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you so much. Participants, kindly please fill up the feedback link in the chat box so that your certificates will be sent to you through your email within 3 days. Thank you.